CSE seminar. Before we start, just a reminder, we are going to have our next seminar December 1st. It's going to be one of our own, John Marshall from MIT. Today, it is a pleasure to introduce to Katie Bouman. So she's an assistant professor in CMS, EE, and the astronomy department at Caltech. Before that, actually, she spent some time here in the Boston area. First, she got her PhD at MIT ECS, and then she spent some time as a postdoctoral fellow in the Harvard Smithsonian Center for Astrophysics. I think that probably most of you are familiar with her work. She's also been recognized with multiple fellowships and awards, and probably you know her as part of the Event Horizon Telescope. I think that today she's going to talk about that a bit. Then regarding a few logistics, so if you have any questions, so I think that the best is that we wait until the end, and at the end you can raise your hand, or if you prefer to use the chat, you can just write it in the chat. If you raise your hand, then I'll just let you just unmute yourself and ask, or in the chat, then we will read the questions. So with that, Katie, all yours, go ahead.
Thanks so much, Adrian, and yeah, thanks for inviting me. I really wish I had been able to make it there in person this time, but I hope to come another time in the not too distant future. Yeah, so as Adrian mentioned, I'm going to be talking a little bit about the first portrait of our very own Milky Way's black hole, and also what we're doing beyond that to see, to continue to see things that are still invisible to us, and learn about black holes in the future. But before we get started, just want to talk a little bit about our Milky Way. So if you go out past the bright city lights, you might just be lucky enough to see the stunning view of the Milky Way galaxy. And if we could travel past millions of stars, 27,000 light years towards the heart of the spiraling Milky Way, you'd eventually reach this cluster of stars. It's right at the center. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped the path of these stars over decades. And what they have seen is actually quite remarkable, because as the stars come very close to the galactic center, they actually get whipped around. So hopefully you saw that they were whipped around by this massive but unseen object that's just sitting there. And by tracking the motions of the stars over time, astronomers have concluded that laying within the orbits of these stars must be a compact object with a mass equivalent to 4 million of our suns. And in fact, this discovery led to the Nobel Prize in Physics that was given in 2020 for the work of Andrea Ghez and Reinhard Genzel, for the discovery of a supermassive compact object at the center of our galaxy. And note that they say compact object here. And so for many years, people have believed that this compact object is likely to be a black hole, an object so dense that its gravitational pull will suck up anything that ventures too close, even light. But at the distance that these stars are orbiting, we really can't say for sure. And so in order to study the black hole, we have to zoom in 1,000 times closer. And there, Einstein's theory of general relativity makes some really exciting predictions for what we should see. So light propagating near a black hole doesn't follow straight lines. It's curved because the black hole is curving space-time, and photons even can go in complete circles around it. And so if this compact object was a black hole, actually the space around it would be lit up by this hot gas that's spinning around. It's heated to hundreds of billions of degrees. And so you have all these photons flying around everywhere. Some of them that are too close or pointed in, they fall into the black hole, but other ones that are farther away get just pulled around the black hole, such that the net effect is that the black hole casts what we call a shadow on the bright surrounding emission that's almost perfectly circular. So we wouldn't expect to see the black hole itself, but actually the imprint of the black hole on all this hot gas around it. But that ring actually doesn't just take on any kind of size and shape. If Einstein was right about general relativity, its size and shape would be directly related to the mass and the spin of the underlying black hole. And so if astronomers were right about that 4 million solar mass compact object being a black hole, we should see a ring of 50 microarcseconds on the sky with not a lot of wiggle room. And so after many decades of studying this mysterious object, just this past May, we actually revealed the first image of this massive body. An image actually that lined up perfectly with predictions from observations in theory. And so this is the first ever picture of the black hole at the heart of our own Milky Way galaxy, which is a radio source called Sagittarius A star, or we like to call it Sag A star for short. And taking this picture, as you'll hear, took this Earth-sized telescope, an Earth-sized team. But what makes taking that picture so difficult? Well, the fundamental challenge is one of scale. Because the Sag A star black hole is so massive, it actually occupies a size of roughly the size of Mercury's orbit around the sun. And that might sound large, but at a distance of 27,000 light years, this is like trying to photograph a single grain of sand. But if that sand is in New York City, and I'm viewing it from all the way where I am at Caltech around Los Angeles area. And so taking a picture of something this small required this international collaboration of scientists from all around the world, building new instruments and algorithms to make it possible. And this also included a big team at MIT's Haystack Observatory, where they've done a huge amount of work on many different parts of the project. And also someone that you might be even more familiar with, Bill Freeman, who is in CSAIL there at MIT. So today I want to tell you a really abridged story of how we were able to take a picture of a black hole. But at this point, you may be saying to yourself, wait, I'm feeling a lot of deja vu. Didn't I hear the story before? And if I turn this image around, it looks a lot like another image you may have seen a few years back. But this is actually the very first image of a black hole ever produced, which our same collaboration published back in 2019. But this is not of the black hole in our Milky Way like the one I showed before, but instead a galaxy 55 million light years away from Earth called M87. And you might think Sag A star and M87 look eerily similar, but actually that's no coincidence. That's actually predicted from Einstein's theory and gives us further evidence that maybe these donuts around black holes are just scattered all around our night sky. But as I said, we published this image of Sag A star like 6 months ago, and the M87 image was published over 3 years ago. Yet these images we recovered from data was actually collected in the exact same week of 2017. So today I hope not just to answer, how do we image the M87 and Sag A star black holes, but also what made imaging Sag A star much more challenging. And I know some of this material I'll say here is going to be a refresher for some of you because I gave a talk a few years back, back when the M87 image was published. But I think it's kind of important to go over the basics here of how we image black holes, because what we'll learn along the way will also lead into 2 projects that I want to tell you about, 2 methods being currently developed in my group at Caltech to push the imaging of black holes past current limits to see things that are still invisible to us. So in particular, I'll be talking today about new machine learning approaches my group is developing for doing uncertainty quantification of images, as well as how we are developing approaches to recover the dynamics of a black hole over the course of a night, even in 3 dimensions. In 3-dimensional space, how is the gas flowing around the black hole? Okay, so let's get started. Again, why was taking that picture of the black hole so difficult? Well, because this black hole shadow ring, that ring that we saw, is just so small and can actually only be seen at a particular wavelength. Actually, if you go back to your high school physics, you can look up like what the diffraction limits are, what are the smallest things we can see, and diffraction limits that require from that wavelength and size that we build a telescope 13 million meters in size in order to see that event horizon scale structure. 13 million meters is essentially the size of the Earth. And so although we couldn't build a single dish telescope the size of the Earth, instead, the Event Horizon Telescope collaboration spent over a decade joining telescopes located around the world to build a computational telescope the size of the Earth that was capable of resolving structure on the scale of a black hole's event horizon for the first time. So rather than building a traditional kind of telescope, now we've turned the Earth into a computational telescope. And so how does this computational telescope work? Well, unlike within a camera, in the Event Horizon Telescope, we don't capture the picture in pixel space, but instead in frequency space. So we essentially are going to be taking measurements of the black hole image's Fourier transform. And if we put telescopes all across the globe, if we covered the globe in telescopes, we would sample all those spatial frequency measurements. But since we only have telescopes at a few locations, that means we only get a sparse number of measurements. And so it turns out for every 2 telescopes in the telescope array, we obtain a single complex measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. But that means that if we only have a small number of telescopes, then we only have a small number of measurements. However, luckily, as the Earth rotates, we obtain other new measurements. Because the projected baselines between telescopes change as the Earth rotates, this amounts to carving out these different elliptical paths in that spatial frequency plane. Okay, so how do we make that image after extracting these measurements? Well, at this point, we have the data, we abstract away the astrophysics, and think of it just as a purely mathematical inverse problem. We have sparse data, and our challenge is to invert the measurements and find the image that caused it. And if we were given measurements that covered the entire frequency plane, that would be trivial, because in the case of no noise, you would just simply need to apply an inverse Fourier transform to the measurements to get back a picture in the end. But we only see a few measurements, and thus there are an infinite number of possible images that are actually perfectly consistent with the data we measure. And on top of that, the fact that there's a different and quickly changing atmosphere above each of the telescopes across our globe causes data to be very noisy, and the problem becomes even more ill-posed. So I just want to give an introduction into what this noise looks like, because it will inform us later in why solving this problem can be so challenging. So the whole reason that this idea works is the fact that light from the black hole is going to travel to Earth for, from Sagittarius A for 27,000 years. And when it reaches Earth, it's going to hit the two telescopes, but it's going to hit one of the telescopes before the other. And that time delay of the time that the light hits the two telescopes, that time delay is going to tell us about that 2D spatial frequency measurement used for image reconstruction. So that's the key for extracting that information. But when you have a telescope in Hawaii and one in Spain and one in Chile, one at the South Pole, they all have different atmospheres above them that causes different random delays in each signal, which leads to an additional random phase delay in each frequency measurement. So now we've kind of lost our phase information here. And similarly, the atmosphere also causes different attenuation factors in the signal, causing a changing absolute gain term. So this error can be really challenging because ideally we would measure this nice, beautiful Fourier component, the italicized V here, but in reality, we have a completely random phase error that's been introduced from the atmosphere. And also sometimes we can have a pretty bad amplitude error as well. And so that's pretty terrible because basically at first glance, we've lost both our amplitude and phase information, right? And what do you really have left if you've lost both amplitude and phase? But there's additional structure here. And if you look at the measurements, remember our measurements come from pairs of telescopes. It's looking at that projected baseline between telescopes. And in the measurements that we get, notice that that we have pairs of measurements, but these corruptions are site-based. They only occur at every telescope. So that means that if we have a third telescope, then the measurements that are formed with that third telescope share some of the same corrupting terms, G2 and Phi2. And so we can design algorithms to try to take advantage of this redundant corruption in the measurements when solving for our images. So if those of you who are familiar with phase retrieval problems, basically this ends up being a constrained phase retrieval problem. Okay, but this still doesn't change the fact that there's an infinite number of possible solutions to this constrained phase retrieval problem. In fact, it means that there are more solutions than we actually had seen before if we just had sparse frequencies. But by injecting preferences for different image statistics into the pipeline, it turns out that you can just whittle this information down from the infinite possibilities to a solution that fits the data and also is likely under some mathematical model of what is a good looking image. Okay, so now in an incredibly hand wavy way, I've told you how you can go from sparse noisy measurements to an image, but how do we actually write that out more formally? And I just really want to show some very, very simple math because I think it's going to just come in handy later, but really, yeah, just really, really simple here. So we're solving an optimization problem where we're trying to find an image X here that maximizes the posterior probability conditioned on the observed measurements y, right? So that's what we're trying to find, that best image in this case. And just by simply rewriting this using Bayes' rule, we can see that maximizing this log posterior probability is equivalent to maximizing the sum over the data log likelihood and the log image prior. So those are just those two terms that I just discussed in this super hand-wavy way. The first one being the data fit, and the second one being the image likelihood under a mathematical model of like what is a good looking image. Okay, but notice that even if we can develop methods such as these to recover a single image from our data, we always have to be really cautious. And that's because any imaging method we come up with, whether it's a regularized maximum likelihood approach or a fancy new machine learning approach, it's always going to require that we inject some additional information into the problem about what images look like to recover something back in the end. And in the case of the regularized maximum likelihood the problem that I'm showing here, it's through that prior highlighted in yellow, this image prior. And this injection of additional information always is going to bias our final image. And for instance, we wouldn't want to have a preference for ring images and then be happy that we recovered a ring back in the end for the black hole, when that is kind of what we're testing, right? And so that meant a big question we faced in dealing with the black hole data was not just how to make an image, but how do we verify that what we are reconstructing with our imaging algorithms is real? But actually, nearly everything I've said so far actually holds true also for imaging the M87 black hole. So before going into how we image Sagittarius A, let me just do a really quick overview of some of the steps we took in imaging the M87 black hole. So as I said, we had to be very cautious when making images, and therefore we tackled the imaging through a multi-step process, a process that took over 1.5 years to complete, that included many synthetic data tests, strict blind imaging procedures, and also objective learning of imaging parameters. And so the first step of this process was to evaluate the methods that we developed on collections of synthetic data that tested our methods in every which way. And this helped us understand where they worked and where they didn't. And one thing we learned from these tests is, as you might easily imagine, is that no method is perfect, right? All methods are going to have their biases. And so it's important to try to assess the commonalities and differences between images recovered under different methods. And so once we, with this insight, once we got the data, we didn't just take one method and make a picture, but instead we developed 3 different imaging pipelines, and we designed these pipelines to have different not hyperparameters on them that control modeling and optimization choices used when solving for the best image. And typically these hyperparameters are tuned by a human user, but instead of having a human tune them, we instead wanted to search for the best set of knobs to recover different types of source structures, and then see how these settings influence the M87 images we recovered. And so for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky with no hole in the center. And then we found the best parameters to recover this disk shape. And then when transferring these exact parameters onto the M87 data, we found that although we had tried our hardest to find parameters, imaging parameters that recovered a disk with no hole in the center, our algorithms in the data still required us to put a hole there when using the actual M87 data. And so by doing this very simple training and testing procedure on different types of underlying sources that we thought could trick us, we saw that our methods always kind of preferred that ring shape. And that was true no matter the day we observed M87 on or the imaging code that we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed everyone back in 2019, this ring of light surrounding the black hole, roughly 40 microarcseconds in size and brighter on the bottom than the top. So our goal here was to try to remove human bias from the final image as much as possible. And we did that by using this simple training data to select hyperparameter modeling choices. And this did prevent us from tweaking those parameters too much by hand to get an imagine that we wanted, an image that we wanted in the end, even if we were just doing that kind of subconsciously, right? And by doing that, we did get this ring shape, which was incredibly exciting, as it was, predicted for many decades, but never actually shown before then. However, this doesn't actually answer the question of what is the uncertainty of that image. How likely is it that that image is actually a ring? And did we just get lucky with those particular parameter choices? So how do we go about doing that? So previously I talked about how we selected one set of parameters, beta, that perform best on synthetic data. But why really should there only be one parameter set that we consider? And in fact, by doing large parameter surveys, we often found that there are many parameters that perform reasonably well on synthetic data sets. So instead of selecting just one set of betas, we instead set a threshold and found all the beta parameters that perform above that threshold on synthetic data. So for instance, for one of those imaging pipelines I talked about, we ran hundreds of thousands of different simulations and found about 1,500 parameters that we deemed acceptable by their performance on the synthetic data. And then we could apply those 1,500 parameters to the M87 data to get 1,500 different images of M87. And once we had this set of images, we could look across them for variations. So on the left, you see the mean image, and you can see that's the average of those 1,500 images, and you can see that ring shape again popping out. But in the center, you can see the standard deviation. And in the standard deviation, you can see that there are different regions along that ring that are brighter than others, meaning that there is more uncertainty in the exact pixel value, the intensity value along the ring in those certain locations, in those not regions that you see along the ring. But actually, if you look at the amplitude of the standard deviation relative to the amplitude of the mean image, so you kind of look at it, you can look at it as a fractional standard deviation here, you can see that actually that standard deviation is quite small relative to how bright that ring is. And so actually it turns out that within the 1,500 images that we created, they basically all contain these ring structures. But what changed a lot was all that wispy structure on the outside. So you shouldn't believe any of that wispy structure you see, but that ring structure, the general shape of it and the fact that it was brighter on the bottom than the top was very consistent across the data, across the images that we produced. But what I want to strongly highlight here is what we're doing through this procedure of having these different hyperparameters and seeing how they affect the image is we're probing different modeling choices and seeing how that affected our results. So in the regularized maximum likelihood problem, we're essentially changing something like our prior term and seeing how that prior affected the results that we got. And that's definitely something that's important to explore because we do have uncertainty in what that prior should be, you know, especially when we're looking at something like a black hole where we don't want to make a lot of assumptions about what it looks like, right? But it's important to note that this is not a posterior distribution. It's not directly quantifying uncertainty due to the data under a fixed prior model. So to explain like why that's so important, for those of you who are, you know, I'm sure many of you are familiar with non-convex problems. And oftentimes for these kind of non-convex problems, which the black hole image problem does, it does turn out to be a non-convex problem. And you'll notice that in these problems, the energy landscape that you're optimizing can be very bumpy, right? And so finding a global maximum in these kind of non-convex optimization problems is a challenge. But even if you're super lucky to solve that optimization problem well in order to find that global maximum, there's nothing to say that there's not another solution that's almost as good that you shouldn't also be considering. And so this ends up being a real significant challenge, especially for black hole imaging, where because we're solving this constrained phase retrieval problem, the problem is non-convex and the energy landscape can be really, really bumpy. And so just to drive that home, here's an example, a synthetic example of black hole imaging. So here on the left side here is a synthetic image of a black hole. And we took this image and we generated synthetic data from it as if the Event Horizon Telescope were seeing this image on the sky. And so now we have this fake telescope data. And using this mock data set, we ran our typical regularized maximum likelihood methods and saw what result we got. And we noticed every time we ran the method, we just started with a different initialization, but every time we ran the method, we would recover different results. In some of the images, the bright spot was on the top right, and in some cases, the bright spot was in the bottom left. And by evaluating the data likelihood, actually it appeared that both modes fit the data pretty well, even when we included like a posterior, or like even when we used something like a total variation posterior, we couldn't tell which one actually was better here. And that's not that rare of an occurrence because of the crazy noise we experience. we have to solve this non-convex optimization problem. And sometimes that does result in multiple solutions. Of course, we know in this case that the true image, the bright spot is in the top right. But of course, when we're just looking at data that we collect from the sky, we have no idea, right? And so this can be a bit scary because it means that we have to, in this case, we have to manually explore the space of possibilities. And if this was real data and we didn't do this, we could be missing out on another image that would lead to a totally different scientific interpretation. And so for problems like this, it's so important that we have ways to efficiently visualize the space of possibilities. So in other words, instead of computing a point estimate like the regularized maximum likelihood optimization does, we want to be able to sample from the full posterior distribution, the probability of X given Y, in order to visualize the full solution space. And oftentimes posterior estimation is achieved using sampling methods such as Markov chain Monte Carlo. However, the sampling and rejection approaches in MCMC can be prohibitively slow and computationally expensive when you're working with really high dimensional inverse problems, like when you're trying to solve for all the pixels in an image. And so to tackle this, we've recently been developing new methods for efficient posterior exploration by exploiting deep learning machinery for the purpose of visualizing uncertainty. In particular, we aim to learn a deep generative model to approximate the posterior samples of an imaging inverse problem. So I'll try to explain what I mean by that. But first, let's start just by really quickly reviewing the deep generative model, and you'll see why in a minute. So I'm sure all of you are very familiar with the great success of deep generative models in computer vision and machine learning. And so what are these? Well, given enough training images, we can train a neural network that takes as input random noise and then outputs a picture that looks like a real scene at first glance. And by plugging in different noise images, you'll get different output pictures. So, okay, why am I telling you about this? Well, these deep neural networks define an implicit distribution over the space of images. And the impressive results that we see from in the generative model literature indicate that these networks allow us to learn really flexible and expressive distributions that can capture complex correlations in high dimensional images. So inspired by these generative models, my former postdoc Hassan, who's now at Peking, and I have been developing an approach to sample from a posterior distribution using a learned generative neural network. So our goal here is to learn the weights phi of a neural network. So we define a neural network and the weights are defined by phi. And we want to learn those weights phi such that if you're going to pass different random input noise Z to the neural network, out is going to pop a sample from the image reconstruction posterior. Okay, and different input noise is going to result in different posterior sample images. So essentially what this network, the goal of this network, its task, is to learn a mapping from a noise distribution to the target image's posterior distribution. Okay, so how can we train this network to give us posterior samples? Well, unlike in the case of like the bedroom generator or face generators that you see, typically, we don't have a training set of images to use. Like if we had a training set of samples from the image reconstruction posterior, then we would be done, right? Because there would be no need to learn a neural network to generate samples of the posterior if we already have those samples. The only data that we have for optimizing the neural network is that sparse and noisy measurement data Y of a single hidden image. So we don't have any images to train with. So in our approach, which we call deep probabilistic imaging, or DPI, instead of using a collection of training images to solve for the neural network, as is typically done in other computer vision problems, we instead found that we could define the loss that is minimized when the weights of the neural network result in a distribution of network-generated images that best match the true posterior. And this can be done by minimizing the KL divergence between those two distributions. Or actually other divergences too. So we've explored other types of divergence and the advantages of using other things like alpha divergence. But for this talk, I'm going to be just talking in terms of KL divergence. Okay, so solving the problem like this ends up actually being a very specific type of a variational method. So as just a refresher, in variational methods, we've defined a simple family of density functions, for instance, Q phi here, visualized by the blue space of possible distributions, where every point in that blue space is a full distribution of images, right? And we want to solve an optimization problem in variational methods. We solve this optimization problem to find the parameters phi hat that best match the target posterior distribution visualized by that yellow star. But then the question becomes, what should this family of variational distributions be? Traditionally, they were pretty simple, so you could solve the necessary integrals by efficiently evaluate probability. So simple distributions like Gaussian distributions are often used. But in DPI, by using a neural network, we can define a very flexible family of distributions parameterized by phi, which are the network weights, right? And this flexible family of distributions can better capture the image posterior distributions that we're interested in targeting because it can capture this complex correlations in the pixels. So here, so you can see that this actually turns out to be a variational formulation of the problem, but actually DPI's optimization problem can also be intuitively derived just by extending the regularized maximum likelihood estimation methods that I talked about earlier. So it turns out that the KL divergence between the neural network's image distribution and that of the true posterior, you can actually rewrite it as this expected log likelihood plus an entropy term. And why is that so important? Well, so the first two terms, these are just the terms that we talked about before that we used to solve a single, the map estimate, right, for the image. So we have our likelihood and our prior. But what that entropy term allows you to do is it doesn't just try to find one image, it tries to find a variety of images. And why is that important? Well, if you don't have that entropy, your network is just going to collapse. So no matter what noise you plug in, it's always going to try to spit out the exact same image that maximizes the posterior. But this entropy forces it to find a variety of different images, right? And so that means in addition to understanding DPI as a variational inference method, it can also just be regarded as a natural extension of doing uncertainty quantifications for regularized maximum likelihood estimation problems. Okay, so now that we've laid out a way that, okay, you can use a neural network to kind of solve this posterior, but actually in order to solve this problem, we need our generative model to be efficient in both generating samples and evaluating the likelihood of an arbitrary image. But many generative models like GANs are only good at generating samples, but you can't evaluate a sample's likelihood to compute the entropy loss. So in order to accomplish both goals, in DPI, we use an invertible generative model. In particular, here we're using a normalizing flow network, but there are other networks like the more recent diffusion models that could potentially be used for this in the future as well. So, and when you have an invertible network, it can be executed in both directions. And as a result, we can easily generate samples from the noise using a forward pass and easily compute the entropy loss using net inverse pass. Okay, so how does this actually end up working? Well, let's go back to that black hole example that I introduced earlier. So remember, for the ground truth image on the top, there ended up being multiple solutions that the regularized maximum likelihood would converge to and we would reinitialize. And we test our deep probabilistic imaging approach on this data to learn an approximate posterior distribution. And on the bottom right are some of the samples from the learned neural network. Remember, we only have one data set Y. We don't see these regularized maximum likelihood images in the training. We only have one data set, and we train our network to approximate the posterior, and then we just pass noise through our network to get those samples that I show on the bottom right. And so you can see that our learned network is actually able to capture a posterior distribution that also indicates there are two modes in our data. And it didn't require any manual tuning or initialization or anything like that. It just naturally falls out that we can see this multimodal distribution. But perhaps the most interesting is what happened when we run it out on some real data. And so this is the result we got when we ran the approach on the real M87 black hole data. And what I find really encouraging is that if you compare the standard deviation in the resulting images to the standard deviation we had published earlier, you can see that they're amazingly similar. And so this was really exciting to me when I saw this result, since the very first time He ran this method on the real M87 data, he got nearly the same result that it took a whole group months to achieve through these grueling parameter surveys. And it actually only took about 1 hour of training time on a single GPU. So I'm really excited to making progress in methods that allow us to better understand our uncertainty in these computational imaging systems. And as it turns out, we found this DPI framework is not just useful for black hole imaging, but very useful for many different types of problems. Here are just a few applications we've been using it on our group, from seismic tomography to exoplanet orbit fitting. But for now, let's get back to the black hole. So the image that we published in 2019 was actually not one image from one method, but an average of images from different methods that all pointed to that same asymmetric ring structure. So, okay, that process seemed to work really well. So now on to Sagittarius A. But it turns out that it actually wasn't that simple. Imaging Sagittarius A was a lot more challenging. Why? Well, even though Einstein's theory of general relativity says these black holes should act the same, from our perspective on Earth, these black holes are actually very different beasts. Sagittarius A is much closer to us. So that means that even though these black holes appear about the same size on the sky, if you actually factor in the distance to each of them, then the actual physical size of Sagittarius A is much, much smaller. Sagittarius A takes up a physical size smaller than Mercury's orbit, while M87 size would extend out past Pluto's. And so remember, surrounding these black holes is this turbulent hot gas spinning around, and that hot gas is spiraling around these two black holes. It's going to move at roughly the same speed, but where gas takes days to weeks to orbit the larger M87, in the much smaller Sagittarius A, it's going to complete an orbit in just mere minutes. And so here you can see two videos of a simulation of Sagittarius A and M87 moving with the same clock as we would see from Earth. And so why is that motion that we get in Sagittarius A so challenging? Well, that means that as we were collecting data during the Earth's rotation, the material is swirling around the black hole so quickly that Sagittarius A's appearance is changing from minute to minute. So now, rather than all the measurements we take over a night being captured from the same static image in the sky, as was the case for M87, now for Sagittarius A, every measurement we get is from a different snapshot of the black hole video. And so we can't simply throw the measurements all into one pot and expect them all to point to the same image in the sky. So now that we don't just have to deal with sparsity and noise, but also we have to deal with some way of dealing with this time variability. And each of those decisions, again, is going to bias our final picture. So how should we get the range of possible Sagittarius A appearances? So one way we dealt with it is by developing 4 different imaging pipelines that would survey how the image would change as a function of different imaging settings. 3 of these pipelines attempted to characterize the epistemic or systematic uncertainty due to modeling choices, like the image prior or variability model. And that 4th pipeline had a goal similar to DPI, estimating the aleatoric or the statistical uncertainty. And in particular, similar with M87, those first 3 surveys have different hyperparameter knobs on them that control those optimization and modeling choices. As you can see, these surveys now included not just how to decide what makes a good looking image, but also how do we deal with the variability in our data. So we had different models of how the image could vary and wanted to see how those models would affect the images that we got out. And once we set up these surveys, we surveyed nearly 175,000 different hyperparameters and saw how those imaging choices affected the images. Again, we identified a collection of imaging parameters that performed well across synthetic data. So of those 175,000 was whittled down to about 10,000 different parameter choices. And then once we had those parameters, we could apply them to the real Sagittarius A data to see the range of appearances we got. And when we did this, this is what we saw. This huge collection of different types of images, where each of the images was actually, each one here is consistent with the Event Horizon Telescope data, but as you notice, each is slightly different from one another. So in order to emphasize the common features appearing in most of the images, we actually averaged them together to get the picture that was the image that made the front pages of the newspapers. And here, this bright ring really clearly pops out. But it's important to note that not all the possible images actually looked alike. In fact, we found that we could cluster the recovered images into 4 categories based on similar visual features, and 3 of these clusters contained a ring-like feature with only differing brightness around the ring, But there also existed a much smaller fourth cluster that contained a variety of images that did not appear ring-like. How much smaller was that? Well, roughly 98% of the images that were created had a ring-like feature, while 2% were classified as non-ring. So the vast majority of the images contain that ring feature. And so this fact, along with many additional tests that I don't really have time to get into now, but I'm more than happy to talk about it during the Q&A, eventually led us to the following conclusion, that the Event Horizon Telescope data of Sag A star shows compelling evidence for an image that's dominated by a bright ring of emission. And so although we can't say anything with absolute certainty, and error bars are all important in science, I think that too, we feel that there's still a lot of evidence for this ring structure. And once we felt confident that with this, that ring structure is really likely to be there, we then moved on to interpretation. And the ring that we recovered actually had, and found that the ring that we recovered had a diameter that perfectly aligned with prior observations in theory. So this was really exciting because two completely different views of the black hole, one relying on the motion of stars that I showed at the beginning, and one relying on the bending and capture of light, they actually ended up being perfectly aligned, which was an extraordinary validation, continuing validation of general relativity. And on top of that, what I find really exciting is that originally those stellar orbits, the star orbits, predicted this 4 billion solar mass black hole. But those 4 million solar masses were only constrained to be within the orbits of the stars, a size 10 billion kilometers across. But now with this Event Horizon Telescope image, we have constrained those 4 million solar masses to be within 40 million kilometers. So this factor of 3 orders of magnitude smaller, and we're much, much closer now to saying with absolute proof, it's no longer just a massive compact object, but in fact a black hole. But even further than just testing general relativity, we find that by comparing this picture to simulations scientists have made for years, the image that we took is incredibly consistent with a number of these predictions. But also there were some surprises. So remember how I talked about how it's evolving over time? Well, we found that the computational astrophysics we've developed way over predicted the amount of variability that would be in there. Our black hole was a lot quieter than we expected. It's still moving for sure, but not with as much turbulence as we had predicted. And so the next step then to try to understand this and to try to improve our models and understanding black holes can actually cover the evolving structure of the black hole. Could we use the collection of different measurements that we collect overnight, not just to make an image of the black hole, but actually a black hole movie? So what we could do this is we could try to break up the data into chunks corresponding to different times and take an image from each chunk of data. In essence, reconstruct each frame of the black hole movie, but this would lead us to too little data to produce high quality images. And instead, what we've done is try to develop methods to reconstruct full movies of the black hole evolving over time. But if you think recovering a static image is a hard ill-posed problem, this ends up being orders of magnitude more challenging because we have the same amount of data, but now we have to solve for the pixels in the full movie rather than just a single frame. And so to get around this, we include temporal regularization, where that regularization controls the continuity that we impose from frame to frame. And we can crank it up and down the amount of continuity to try to find movies that fit the data, but allow for more or less variation. And so now with these methods in hand, we went to go reconstruct real movies of the Sag A star data. However, we found that when we went to make the movies, we could actually, although many of the parameters would get very consistent movies, there were some parameters that we could get a very different movie out, and it still kind of fit the data reasonably well. And so those results showed us that while the image of Sag A star exhibits interesting and measurable dynamics, our current methods can't actually conclusively determine the evolution of Sag A star over those short periods of time with the current data that we have. And so this highlights that as important as it is to continue pushing on algorithmic approaches like this to squeeze more out of our data, it's important to realize that also to extract more science, we also have to think about not just improving our algorithms, but also our instrument that collects the data to begin with. And to that end, we've been working on improving the actual Event Horizon Telescope network. So in 2017, we observed with telescopes at 6 different locations, And since then, we've been building our array to get more data, adding telescopes in Greenland, France, Arizona. And then the one I'm most excited about is we're adding a telescope at Caltech, Caltech's Owens Valley Radio Observatory. But what could we do if we added 10 more telescopes? Well, maybe we could actually make a video of the gas falling into the black hole that we actually believe, a robust movie. And being able to make a robust video such as this would be a huge scientific goldmine. And actually making this dream a reality is now being carried out by hundreds of astronomers around the globe who are actually just convened this past summer in Spain to push forward this idea, this next generation telescope concept. So I'm now starting to reach the ending of the talk, but I do want to highlight one point that I think is very important. And that's that I believe this effort really concretely highlights that there's this two-way street between science and computational algorithms. And many times in computational fields, we go to our science friends and ask them, what problems do you need help solving? And I think this is fantastic, and we definitely should continue doing that. But I think that also magic really happens when you realize that science doesn't just motivate new algorithms, but in fact, sometimes algorithms can motivate new science directions as well. And so before ending, I just want to really, really briefly highlight another project that we're currently working on that I think I'm really excited about, that I think embodies this spirit. So with the help of computational methods, the goal, what we've kind of been working on recently is, can we recover not just a static image or not even just a movie, but can we recover the emission around a black hole and see it not in 2D, but actually in 3 dimensions? See bright flares of hot gas spiraling in 3 dimensions around this dark bottom. And this imaging capability would not just tell us about the dynamics of accretion, but could also reveal the structure of space-time itself close to the black hole. But how do we go about seeing hotspots spiraling around the black hole in 3 dimensions? Well, we face 2 big challenges that separates it from regular 3D tomography problems that we're used to seeing. First is that our rays are no longer straight, they bend and go in complete circles around the black hole. And second, and most challenging, is that in 3D reconstruction, like when you're doing 3D reconstruction of everyday scenes or like of CT or whatever, typically you have views of the object from all different directions. But in our case, we only have one viewpoint ever. We're only ever going to see the black hole from our perspective here on Earth, and we'll never see another view. And so now we have these gravitationally lensed 2D projections from just one orientation of the sky. And in fact, we have even less than that. We only have sparse measurements of these 2D projections over time. But recently we developed an approach where we're able to show that on toy problems, we're able to take these sparse measurements and use it to help constrain a reconstruction of the evolving 3D environment around the black hole. And how can we do that? Well, by just injecting a little bit of the expected physics back in, by saying, let's say we trust general relativity, but nothing else. We don't trust anything about how the gas looks around the black hole, but we trust general relativity. And to do that, if we impose some of these physical constraints, that actually allows us to jump out of the 2D image plane into 3 dimensions. So Aviad Levis, a postdoc here at Caltech, has been taking a lead on this direction to recover 3D emission around the black hole, but with our collaborators Pratul at Google, Andrew at Princeton, and Ren at Berkeley. And I don't have time to get into the details, but just to give you a rough idea, we take inspiration from very popular work in computer vision nowadays called these neural radiance fields. And we build this whole end-to-end deep learning network that uses our telescope measurements to train both the emission at some time t and the axis of rotation of a physics-inspired flow field. And those parameters are trained jointly. And using this network, we show that there's actually promise in using such an idea to recover the dynamic flares exhibited by Sagittarius A over short periods of time. And one other thing I want to highlight is that although doing this analysis requires us to inject some knowledge of physics back into the problem, it allows us to have flexibility in what we're recovering. So here we're recovering just random digits, the numbers 0 through 3, rotating around a black hole. Obviously, we don't expect something like this to be happening, but it's pretty exciting that we can kind of trade off on the spectrum of model fitting to full image analysis here to recover these non-parametric emissions that could potentially enable future scientific discovery. So overall, this is a super, super early stages, just a proof of concept, but we believe that this work demonstrates promising first steps towards the scientifically important task of recovering 3D dynamics around the black hole. And I'm super excited for what scientific questions a technique like this would help us answer in the future. So with that, to close, it's clear we've learned a lot from these images of Sagittarius A and M87 already. But what I hope I got across in the talk today is we're really just at the beginning. There's so much to come. Hopefully one day we'll be able to show you not just static images, but actually movies and perhaps even in 3 dimensions. And the main message I hope I got across is also that computational algorithms have played a key role in science, the science we've done, but it's really just the tip of the iceberg. And you know, again, there's this picture I would like you to, I'd urge you to come at problems and solving these kind of interdisciplinary problems from both directions. So with that, I want to thank the amazing team of EHT collaborators that worked tirelessly over the last few years to make this result possible. Particularly, I want to highlight Avi and Pratul, who led the additional projects I spoke about today. And just also talk about that my group doesn't just work on black holes, but many different problems at the intersection of imaging, science, and technology. For instance, seismic tomography, medical imaging, and even using your personal camera in new cool ways. And we're always looking for cool new directions and in the imaging realm. So it'd be great to connect with you guys more in the future. But with that, I'll leave it, and I'm happy to take any questions. Thanks.
Thanks a lot, Katie, for a very great talk. So now the floor is open for questions. So if you want to ask the question yourself, just raise your hand and then unmute yourself. I think that we have already one question is vote up, so just go ahead. Are you there? Yeah, we cannot hear you. So otherwise, while we maybe vote up, it's a problem. If anybody else wants to ask a question, yes, you can also write it on the chat if you prefer, or just unmute yourself. I have one question, like obviously this is not my field, but I would be very curious to know. So if you can right now say, what is the bottleneck? If there is one thing that you would like to fix, so it's related to the algorithms, computing times, the infrastructure, the instrument, the algorithms that we use, or the approaches. So what would be the main bottleneck that is actually that we need to go through to make a breakthrough?
Well, yeah, it's a really good question. I mean, I think it's also is the bottleneck on the computational side or on the instrument side. Maybe I can address both.
Yeah.
I mean, so really, people are really interested in seeing that ring and getting as information about the photon, what we call the photon ring, but also seeing in 3 dimensions, or sorry, seeing in time how matter orbits, and that allows us to put better constraints on general relativity and test it with stronger and stronger tests. In order to get higher resolution, we really need to we're basically at the highest resolution we can get from here on Earth. So to get higher resolution, you'd have to go to space. But if you go to space, there's always we can't have a constellation of telescopes in space. It'd be way too expensive, billions and billions and billions of dollars. And so, but there are ideas of putting one telescope in space, but then you again have a computational problem of, well, how do we fill in that missing information with only one telescope? So there's only so much resolution we can get from an instrument. Other things, so the route that's currently being going down is to put more telescopes on the Earth, and then using that to see evolution more so than getting finer detail. And that could help us put constraints. But from a computational point of view, I think just methods that allow us to, I think we want to explore this spectrum of methods that are completely agnostic to the physics. And that's what we've done with imaging, to ones that start to add it back in and see, well, what if we add little pieces back in, what are we actually able to infer about the space around a black hole and about physics and everything. And so I think there's just a big need for algorithmic development on that end, is kind of a mix between modeling, non-parametric and model-based approaches that infuse physics and machine learning and stuff in order to recover other types of information from the sparse data.
Yeah, and I actually wanted to also ask you about that, because you mentioned about using algorithms or maybe some physics and then merge that together to get a better picture. Are there already in the images that you got any underlying physical assumptions, or are they
Not
general?
in the image work. So in the image work, it's very important that we didn't have any physics assumptions because we wanted to test the physics. So we didn't want to impose any kind of physics model in that. Once we were confident, once we had reached some confidence in the level and that this was a ring structure or something, then we start putting back physics in. And we say, okay, well, so all the imaging results that I showed, just pure two-dimensional images, they have no physics assumptions. But additional follow-up analysis of like, let's fit a ring model, a crescent model, let's fit to these computational models of the fluid dynamics around the black hole. Then we start putting in more and more physics and trying to narrow down, try to get more information out. But yeah, just the pure imaging, we want to be completely agnostic to the physics. Of course, there's physics of light propagation, like how does it hit the telescope, how does the Earth rotate, things like that. But as far as black hole physics, none of that.
Okay, yes, this is just very basic physics that everybody would agree with, essentially, like the speed of light and things like that you will need to use in a way.
Exactly.
Okay, yeah, thanks a lot. Okay, so if there are other questions, yes, unmute yourself, write in the chat. So we have a question in the chat by Jolu. Is it useful to combine stellar orbit data with the EHT data to do analysis?
Yeah, I mean, not to do the imaging, but definitely the stellar orbit data was like essential for us to, for this idea of testing general relativity. So the reason Sgr A has been like kind of the holy grail of this analysis is because there are additional methods that can weigh the black hole, that have been able to basically say, well, there's a compact object with this mass. And that provided very, very strict predictions with very small error bars on what kind of image that we could get out in the end. And so if we got an image that was bigger or smaller than that prediction, then we say, okay, something is breaking down about general relativity as we get close to a black hole. And where we think general relativity is most likely to break down is in this extreme environment around a black hole. So definitely the stellar orbit data was essential for our analysis of the images. Now going forward, are there other things that could be done to try to actually help with imaging the black holes? Well, there's other types of telescopes that we actually observe with at different wavelengths. And so we have these multi-wavelength campaigns that are all observing at the same time. And we learn information from them. For instance, if there's a flare, a bright hot spot that kind of flares up around the black hole during our observing, or things like this. And there's also this collaboration called the gravity collaboration, which can't actually make images of a black hole, but they can track bright spots orbiting. And so there have been talks about also potentially in the future trying to observe simultaneously with some of these other instruments to actually help with the imaging process, not just in verifying what the image actually means.
Okay, we got the question by Gaurav, so there is a very general question. If there is any connection between what we learn from the black holes and then the origin of the universe, if there can be that link with that.
Yeah, well, I'm not the best person to answer that, as I'm not a astrophysicist by training myself, but definitely black holes. One reason that people want to study them is there's always this question of, these supermassive black holes appear at the center of galaxies. And there's a big question of this chicken and egg, do they help the formation of galaxies, or are they produced by the galaxies themselves and stuff? So I think that how they interact with galaxies is a big question. And so learning more about them would help us in understanding that. There are two kind of sides to why we want to study black holes. One I mostly talked about is this fundamental physics side, which is it allows us to try to test gravity in the most extreme environments where it's most likely to break down, as I said. But another is that we just want to learn about black holes. How do they evolve? How do they spit out these huge galactic scale jets? And everything. And how do they interact with the galaxy? And so these are two kind of different reasons that studying the black holes, what we can learn from them.
Is there any disappointment in the sense that everything is matching very well, the predictions from general relativity? Like the opposite would be much more interesting in a way.
Yeah, I think both are exciting, but yeah, I mean, if things were not to match, I think that I think at some point, you kind of hope things don't match if you zoom down enough, right? Because then that is highlighting, well, there's something there that we, that we're not understanding. But just also the matching is pretty exciting. You could say, oh yeah, it's obvious now. But when we started, we had no idea what we would see, right? And so the fact that this theory led to this prediction, that had a theory that had about 100 years ago was pretty, that's pretty, I think, amazing in itself. Also, I think that if it hadn't matched, there's a lot of other things that would come into question. First, are our methods, working and stuff like that. And but I think that the fact that it's pretty amazing that how spot on it's been. But of course, we can try to continue to improve the methods to zone down more on the resolution and all these other things that maybe we'll find a break somewhere. But yeah, so far we haven't found that.
So maybe we have time for one last question, Yolu. So in your VI analysis, did you assume a Gaussian distribution and adopt a mean field approximation? Are you worried about multiple modes in the posterior you may miss in the VI?
Oh yeah, so the whole point of the fact that we use the neural network for parameterizing that variational inference problem is the fact that we don't have to stick with Gaussian distributions. So we don't have to do something like mean field or anything like that. We can get these much more complicated distributions. And so that allows us to not just have these multimodal distributions, but also just complicated kind of distributions. And so that's the big advantage of using this deep variational, deep probabilistic imaging, where we use a neural network to capture that distribution. And as far as multimodal distributions, there's always, we show in the paper and how I showed also in the results, we can get multimodal distributions. But there's always a problem if you have really high dimensional spaces and you have many, many modes. Sometimes these Kale divergences can, that loss can miss some of the modes. So there's always this problem of mode missing. I forget the term, but yeah, but that's why actually we have some follow-up work where we talk, where we use something called alpha divergence instead. And that allows you to trade off exploration and exploitation in solving for the parameters of the variational distribution the neural network gives, and allows us to capture more, like we can capture multimodal distributions even with the Kale divergence, but even more so with the alpha divergence, it makes sure that we don't miss them. And so, yeah, I encourage you to take a look at that.
Well, thanks a lot, Katie, for the talk, for taking the time to visit us virtually. Hopefully next time we can see you in person.
Yeah.
So yeah, it was a pleasure, and thanks to all of you joining the talk. So see you next time. Bye bye.